Hi, my name is Shende, and I'm excited to be presenting my research on using glitter as a single image camera calibration object here in this virtual setting. In this work, we use a characterized sheet of glitter to achieve competitive camera calibrations. Our lab setup includes a flat sheet of glitter seen on the right, a monitor which serves as our light source seen on the left, and a camera. Characterizing our glitter involves displaying multiple scan lines moving across the screen and tracking which glitter pieces are lit by each scan line. For each glitter piece on our glitter sheet, we can intersect a set of scan lines to find the point on the monitor which lit that glitter piece. We draw the ray from the light source to the glitter, and the ray from the glitter to the camera, and compute the surface normal. We do this for all of the pieces of glitter on our sheet, thus giving us what we call a characterized sheet of glitter. At calibration time, we start with a picture captured from a camera. We use CalTag markers to map this picture into a canonical coordinate system. This allows us to find and match glitter pieces across pictures taken from different cameras and different positions. For each glitter piece seen in our image, we find the closest characterized piece of glitter. Each of these glitter pieces then has a known surface normal, which we can use to draw a reflected ray. In the first optimization, we compute the intersection of these rays to find an approximate camera translation. Those rays that form a clean intersection, shown in blue in the bottom left image, are considered consistent and are used for the glitter error. Some glitter pieces are rendered inconsistent because they either have been incorrectly matched to a characterized piece of glitter or were not characterized at all. Then we assume that this translation from the first optimization is correct and optimize for the rotation and focal length using the CalTag error. Finally, we optimize for all three parameters, starting with the final values from the second optimization, using both the error obtained from the CalTags and the error obtained from the predicted intensities of the glitter pieces. These next three slides show short visualizations illustrating how each of the three optimizations work. Here we see the first optimization, solving only for the translation based on the glitter error. For this, we compare the predicted versus measured intensities of the consistent glitter pieces. Given an assumed geometric setup, we draw the ray from the light source to the glitter piece, reflect this ray based on the known surface normal, and compute how close it gets to the camera pinhole. Multiple effects determine the brightness. The light is not a point light source, the camera has a finite aperture, and the glitter piece may not be completely flat. For simplicity, we model these effects as having the observed brightness of the glitter with a Gaussian profile whose intensity falls off depending on how close the ray comes to the camera location. Next, we see the second optimization, solving for the rotation and focal length based on the CalTag error. For this, we want to minimize the average distance between the predicted image projection of the markers and the actual image coordinates of the markers. This is the final optimization. On the left, we see the ground truth camera translation and focal length obtained from the Zhang checkerboard calibration. On the right, we see the predicted translation and focal length at each iteration of the optimization. As the optimization runs, the predicted CalTags align with the actual image coordinates, and the glitter intensities form more of a diagonal, thus minimizing the error. And we see that the translation and focal length approach the ground truth values. These are results from two examples of several different experiments. The top result is a calibration of the characterizing Nikon camera and a different location, and the bottom result shows a calibration of a different Sony camera. The left image in each figure shows the light source, the lit glitter used in the calibration, and the final frustum of the camera. The middle and right images in each figure show the final CalTag alignment and predicted glitter intensities for the calibration. This table shows all 5 camera results, ground truth in green and ours in blue. We can see that for each of the Nikon cameras, we achieve results that are within the error bounds of Zhang's checkerboard calibration. The Sony camera results are close, but not within the error bounds. We discovered that the Sony lens has more distortion than the Nikon, something that we had not modeled. This is a limitation which we will address in future work. Geometrically, we have been working with a pinhole camera model. We are working on approaches to model both pincushion and barrel camera distortion in our calibration. Earlier, I mentioned a glitter error in which we predict intensities of the glitter and compare these predictions to observed intensities. We have implemented a very simple model to compute these predictions. In future work, we intend to more completely model the imaging pipeline to explore what else our glitter can tell us about the camera with one image. Thank you.